Of course it is. So, although question A is a straightforward work energy or conservation of energy question, question C, you need to know more. And question C doesn't actually ask you what the maximum speed is, which would actually be a more interesting question. So keep in mind, if I were going to ask this on a test on Friday, I would want you to calculate what the maximum speed is, because I think it requires several important details that students tend to leave out. But it didn't ask that. It just asked the distance the spring would have to be compressed at the instant the block makes it to its maximum speed. Well, that's when the net force on the block is equal to 0. So that occurs when the downward force of gravity from the block is equal to the upward force from the spring. So in this case, that's going to be kx equals mg, or mg divided by k. 2 kilogram block, if I use 10 for g, it's going to be 20 divided by 200. So 0.1 meters. Now, a more interesting question is to figure out how fast it's going there. And the reason I say that is because that is, I don't know how far that is based on the drawing here. This is out of proportion, but I would say if this represented how far the spring was compressed when it makes it to its maximum speed, if you're trying to figure out how fast it's going, you have to realize that this becomes the new reference level for computing potential energy. So if you wanted to try and do the discussion of work, which is what I would, what we've talked about so far, you'd have to say that the work done by the spring plus the work done by gravity would have to equal the change in kinetic energy. Yeah, this would be the question I would ask. Say this is C part 2. The work done by the spring is going to be negative because it's pushing up on the block while the block descends. So that'll be negative 1/2 k x squared. While the work on the block by gravity is positive because the force of gravity is downwards and the block is moving downwards, which is going to be 2 times 10 times, in this case, it's h minus h naught, where we've set this to be 0. So that'll be 0.55 as the total displacement of the block until it reaches this point. That's how much work was done. And that would have to equal the change in kinetic energy of the block. Assuming the block started from rest. Now, is there any questions to this point on what we've written here? Because I'm going to come back to this in like 2 minutes. I don't care what the answer is. This is how you'd find it, though. And the important distinction here is having to know that we've reset where that reference is. This has to represent the displacement of the block due to the force of the spring. So it's the force downwards times the displacement downwards. Now, question D says determine the maximum compression of the spring. Well, that's a little different. I don't know where that occurs. Let's just say it occurs someplace here. I'll call it X. And that's where the block finally comes to rest against the spring. That means there's going to be work done by the spring plus work done by gravity, but that's going to have a change in kinetic energy of 0. The block comes to rest at the point where we're at the maximum compression of the spring. So if I wanted to figure out that maximum compression, the spring is still doing negative work on the system. But the block, on the other hand, is having positive work done by gravity. And again, that force is going to be 2 times 10 times the displacement, which is 0.45 plus x. And this has to sum to be equal to 0. Now, it's a quadratic. You're going to have to deal with the fact that the reason it's a quadratic is because there are 2 possible answers for x, but one of them doesn't really make sense in this instance because it represents the positive displacement above the reference level where the system might come to rest if the block were to stick to the spring. So find your 2 answers, but one of them's positive and one of them's negative. I believe in this case, we made downwards positive, so we want the positive answer. Is that enough, or should I do more of this problem? Your silence is golden, so I'm going to go with that's enough. Any questions at home? Let's take this for just a minute. All right, I want to just grab that, and we're going to take it to another page and write it back out, okay? It was the energy in the spring minus the energy in the spring. I'll call that elastic potential energy, plus the work done by gravity, which I'll call the gravitational potential energy. And it equaled the final kinetic energy minus the initial kinetic energy. Okay? I'm just taking what we had over there and just naming this the elastic potential energy and naming this the gravitational potential energy. Everybody okay with that? Oops, wrong way. Consider that the problem starts with the spring and the box above it. And this distance is our 0.45 meters. And ends with the box, again, no, this is not that one, with the box somewhere here with a velocity downwards, but the spring has been compressed some distance. Okay, everybody following that so far? At this moment, when it hits the spring, it's moving, so it has kinetic energy. And the spring is compressed, so it has elastic potential energy. When it's at the very top, this is the initial kinetic energy, but it's not moving, so it's 0. But it's above where the spring is, so it has gravitational potential energy. If you look at this statement, it might not be easy to see this, but move everything to the side of the equation where it's made positive. And you'll see on the left side, you get the gravitational potential energy plus the initial kinetic energy has to be equal to the final kinetic energy plus the elastic potential energy. This represents all of the forms of energy that existed at A. And this represents all of the forms of energy that existed at B. In the work energy theorem is conservation of energy. It exists inside the work energy theorem. The statement is the actual statement for conservation of energy. We're going to talk about conservation of energy today, but the things we have been doing here's where they have to interrupt us a second time to tell us to ignore the bell, that they're working on it. But because they probably weren't anticipating that, it's going to take people in the office several moments to figure that out. But I don't think that's an actual bell. What do you think? It's 2:08. I don't think so. I mean, I think it was the sound of the bell, but I don't believe it's the sound that lets us know it's time to move on to seventh period. So we'll keep going. Fair enough? All right. So we're going to be talking about conservation of energy today, but it really isn't something that's going to be considered new. It's a different way of thinking about how we deal with work and energy, but it's not really something that's new. So I'm hoping that we'll be able to go towards that here in a few minutes. But those of you who remember this from last year probably remember a little bit of this. That we can take a look at the energy states at different parts in the problem. And if nothing has been acting to take the energy out of the system, these energy states have to be equal. I'm merely adding up the forms of energy at one place and setting them equal to the forms of energy at another place. All right, so we'll come back to that, but I want you to start thinking about that for the time being. All right, I'm sorry. We're going to talk today about something I don't really want to talk to you about, but it got brought up at the end of class yesterday, so I have to. I'm going to.
Good afternoon, people. Thank you for all your cooperation through the testing with the income system. Have a nice day.
That was a long gap. You guys hear that at home? All right, good. Well, Amanda says we got the interruption letting us know that they're working on the intercom system. I think we had figured it out, but just in case. So we've already talked that if I give you the acceleration of the system as a function of time, that you know how to figure out the velocity. Now, we've had this conversation at the beginning of the year. A student walked up to me at the end of class period yesterday, seventh period, to say, what is this symbol? And I come to recognize that perhaps I should have a more formal conversation here. So I'm going to have a formal conversation in 10 minutes or less to explain to you what that symbol is. And you already know its purpose in a small way, not its entire usage or what its entire meaning is, but you know a part of it. And I'm going to use something that you already know about as a means of conveying this. Now, that being said, I am not waiting until you guys learn this in calculus to introduce it here. As I said yesterday, you are going to have to become equipped. And if that means we have to learn something ahead of time or you have to be pushed out of your comfort zone, so be it. Otherwise, if we wait until you learn the calculus necessary, we won't get to do any of the calculus part of this class until April, 3 weeks before your exam. Do you really think that's a good idea? Because I don't. So I know that I have students in a variety of places when it comes to their math skills. But today, I need to let you know, you're going to have to be pushed out of your comfort zone. But I always look at this as maybe a positive in that you'll be a better calculus student for it. Or if nothing else, you'll upset Mr. Brashear and Mr. Bright because you'll be doing it wrong. That's fine by me too. So let's start by the things I've already had you do. You should be able to write this as a differential equation. That shouldn't be a hard thing. Moreover, I shouldn't have to make it look like this. I could say, net force equals MA. And I could still ask you to write this as a differential equation. Meaning making a differential equation just identifies which variable is related to time or mass. And it requires you making that a differential equation by replacing it with the likely differential. In our case, our differentials are almost always with respect to time. So turning this into a differential equation means just replacing A with dv dt. Now, the next thing, and this is where I need you to understand something. This dv dt has lots of different ways of being represented. I don't have to write it like that. I could write it like this. That's a way of representing it. Take the first derivative with respect to time of the velocity function. That's kind of how that's stated. But it's stating that same thing here. It just looks like a fraction. Why? To make it look like the slope specifically. I've also told you that in college, you might just write this as v with a dot on top of it, because this is kind of hard to write all the time. But all of these things make use of the same idea. We're trying to see how the velocity changes with time. But what we're doing next is actually trying to come up with that function, the function that existed before, the one that tells us about the velocity. And the way we do that is by splitting the derivative. Again, something that we've already talked about, something that my expectation is you can do. It's just multiplying by the bottom of that fraction. Now, here's where I guess I lost some folks yesterday, or they wouldn't have been asking me questions after school. If I want the function of v, I need to do the process that you guys have called so far the antiderivative. But that's actually a part of a larger set of instructions. The truth is, in order to get to the original function, I need to find the integral of both sides. And that's what we were doing yesterday. Now, taking the integral is kind of like squaring both sides of an equation, in that if I wanted to, I could square both sides of this equation, and all of you know that it would require that I take and make sure I square both things. Taking the integral of both sides is a similar thing, but it's more similar to maybe taking the logarithm of both sides. And the logarithm is a process. The integral is a process. So I put this symbol here. Now, don't put too much investment in what this symbol means. It is supposed to look like an S because it represents the summation. Now, I know you guys who finished AB already know all about that, but you guys who are in AB right now, you're not there yet. You will be. You'll learn to hate it because you're going to actually sit and sum many functions. That's what you're going to do for a little while. Draw little rectangles and add up all the rectangles to get all the area. If you're there now, you're probably loving that. No, it's boring. We're here to figure out that you don't have to do that. That if you understand how to take an integral, you don't have to actually add up all the individual areas. But there is a standard way that this gets written to let us know what all the symbols are meaning. So every one of those blanks or squares represents a place where a number or an expression is placed. It's the symbology, and it's how the symbology is used. First, this is called the integrand. It's the function that we are about to address. This tells us which variable is the one to which we are taking the antiderivative. It's important because in our classes, everything else is considered a constant except for that variable. Someday, perhaps, you'll have to take partial differential equations, but that will no longer be true. But for today, that's true. These represent boundary conditions. More or less, they tell us where our sum begins and where our sum ends. Because what we have found is that doing this process actually returns a sum of the area of the function. That's what it tells us mathematically. It's an area under a curve. But physically, meaning the physics behind this, it tells us specifically what the prior function was and applies starts and stops to that function. So for us, when we do this, we address both sides of the function. And before we go on, we make some identifying information here, meaning we indicate that we observe this occur at time 0. Where the boxes are represent the beginning and the ending time, because time is the variable here. And on the V, it's going to be the beginning and the ending velocity. So at time 0, the object had initial velocity V naught, We've been using V naught as a symbol for initial velocity all semester. The top represents the final part, the final boundary. We're going to say sometime in the future when it has some final velocity. Now, I know some of you don't like the fact that this letter, and it's all the same T. I know. That's because we're creating a function with T in it. That confuses you. Use something else, but T works really good for time. Just like here, we're creating a function with a final velocity in it. It makes sense to have V in there. So the limits, which is what those are called, the boundaries, we don't actually use those right away. We use those at the end. But I'm stating to the person grading my paper that I understand that it's going to have some velocity at time 0. I'm linking that together. And some velocity at some future time. I'm linking that together. I need, when I take the integral of both sides, to link those things together. But all of this just represents the symbology that's used to take the integral, which will give us the prior function. Before, when we did this, I made some concessions. I cut some corners. Why? Because it was the second week of school. I'm no longer cutting the corners. So we go forwards now. This part, you employ the antiderivative here. Depending on what's there determines how you do that. The more complicated the function, the more difficult it might be to find the antiderivative. Our functions are relatively straightforward in mechanics. They might not always be, but they are right now. So this is a polynomial. Not a whole lot to do here except take my exponent and add 1 to it, and then divide my coefficient by the new exponent. We learned that in August. But now that I've done that, I've taken the antiderivative, but I've not employed the limits. I need to make sure I remember to employ the limits. Place them there. On the other side, there doesn't appear to be a function, but there's always a function. So if there doesn't appear to be a function, then the function is 1, expressed in terms of my variable, v to the 0. That's still 1. Now I still employ the same antiderivative work I did before. I add 1 to the exponent, and I divide by my new exponent. I still wrap the boundaries. So I have effectively taken the integral of both sides. Not quite done yet, but there's really not a lot to do. I now have to invest my boundary conditions into my new function. I have to take and put v minus v naught. Put the first variable in, and I subtract when the second variable is put in. Or put the first boundary condition in and subtract the second boundary condition. On the right, that might make a little more sense. It's going to be 2t cubed minus 2 times 0 cubed. Put in this condition first, then this condition, and subtract them. What I'm left with is my function, but I should solve for the function that was asked of me, which was the velocity. That's my function. It says the velocity is equal to 2 times the time cubed plus the initial velocity. So I've done what was asked. That's what the mathematics returns. That's what finding the integral is about. So if I take the integral of both sides, that's what I'm doing. The thing that was hard yesterday was I didn't have something that was a simple polynomial. I had something that was a little more complicated, had a little more gusto to it. Look, these can be impossible to take the antiderivative of. There are functions to which the antiderivative doesn't exist. That's why in Calc 2, you'll learn about Taylor expansions and infinite series and garbage like that that just makes math mean. because sometimes you just have to get an estimate because you can't actually get an answer. All of our functions are going to have a polynomial answer or a trigonometric answer. They're going to work. Not necessarily true in EML.
Only this interruption because we're still testing the intercom system. I will be doing a manual bell. Please disregard the bell. Thank you for your cooperation.
So you do have to understand, though, that sometimes there are just functions to which an integral is part of the definition. And this is one of them. The definition of work is an integral, which means you might have to take the integral. You'll notice the integral is only on one side. That's okay. It's not going to hurt too much. The truth is, if you want, we could write it as an integral on both sides, but I don't think you need to make it more complicated than it is. But I do want you to understand that if you have a function whose definition has an integral in it, it is telling you to be careful. It is specifically, this one is specifically telling you to consider whether either of these variables change as the object moves. That's what it's telling you. Be careful. If one of those things changes as the object moves, you need to find the function with respect to the position. Or in this case, it could be the angle with respect to the position. You need something. Because if the angle's changing when object moves, you need to find out how. And if the force is changing when the object moves, you need to find out how. You can't find out the work without knowing that. And just so you know, it doesn't have to be hard or weird. There's definitely examples where that can happen. That's not just too terribly complicated. Believe it or not, I use this in the test for AP Physics 1 this year. So what if I had a rope that passed over a pulley to a guy that's standing over here, and he's just going to pull on this rope. The box is going to slide to the right. Everybody agree? Do you realize that as the box slides to the right, this angle is going to change? So even if he pulls with a constant force, he's going to be pulling in such a way that as the box moves, the angle is going to change. It changes every single time. Now, do I know how the angle and x and theta are all related? No, not yet, but I could probably have to figure it out. Probably could figure it out. Probably something with hypotenuse and square roots and stuff. But I'm not asking you to do that. I'm saying, can you imagine a situation where there would be a function that would describe the angle changing as the box moves to the right? Because that's what would happen here. I would not be able to calculate the work without doing the integral. Now, is this on your next test? No, this would be hard. I'm not trying to make it hard. I'm trying to tell you, when do you have to integrate? That's what you have to be able to figure out. So if this changes while the object's moving, you have to integrate. We had an example of that already. Our example of the one that we actually did in class. When the box moved to the right, the force required to move it changed, right? It took more and more force as we moved it to the right. That required integration to figure out how much work was done. All right, that's all I want to say about it, which was way more than 10 minutes. But I want to be very complete that you have got to understand that we're not going to ignore this. You have to look at the problem and figure out whether you need this or you don't. I'd love to tell you that there's always a cop-out, that there's always a way to say, well, just find a change in kinetic energy. That'll make it easy. Sometimes you just can't. Sometimes you have to evaluate the force. Sometimes you just have to. So that's all for that. Let's talk about something that is actually probably one of the easiest subjects we have all year long. The only thing easier than this is conservation of momentum. So today we're going to talk for the remainder of the class, however much that is, about conservation rules. Of which there are two. These are not the same, which is why I'm kind of writing them separate here. They're not the same. We're going to talk about conservation and conservation rules, of which there are actually lots of conservation rules we believe in physics. There's conservation of charge, there's conservation of energy, there's conservation of momentum, there's conservation of molecular spin, there's conservation of atomic spin. I mean, there's a lot of conservation rules out there. We're going to focus on 4 this year. We'll have 4 conservation rules this year. And the first one is conservation of energy. And the most important thing about all conservation rules is the word conserve here means stays the same. That's what it means. You've already had conservation rules. You had them in chemistry. You might not have always remembered them in chemistry, but they were there. The conservation rules in chemistry tended to deal with things like you're going to have the same number of atoms on each side. So the number of the count. So if there was 4 carbon atoms on the left, there's going to be 4 carbon atoms on the right. That was a conservation rule. And it wasn't conservation of mass, it was conservation of molecular identity. It had to exist on both sides. These are the same, in that conservation rules mean that something stays the same. Conservation of energy isn't just a rule. We believe that's a law in nature, that energy is conserved in all forms, in all different processes throughout all of nature. That doesn't mean you know where the energy went. We're just saying that the energy is neither created nor destroyed. Now, nowadays, we have added to this that our conservation rules have to include the fact that mass and energy represent 2 sides of the same thing. So when we say that it's conserved, we say the total amount of mass and energy in the universe stays the same. But that's really a nebulous idea. We're going to focus on the idea that energy is conserved and it flows from one form to another. But that doesn't always mean that the energy that we see in a system is useful or can be reciprocated. Meaning, I can push on a spring and get that energy back, but if I scrape a box across the ground, I'm unlikely to get that energy back. Some energies I can reciprocate. I can get right back out of the system. And some energies, once changed, are difficult to change back. So if we lose energy in the form of heat, it's hard to get that energy back. There are some forms of energy, though, that we get a one-to-one reciprocation. And those are the parts that are important. And we call those mechanical forms of energy, where we get a one-to-one reciprocation. I mean, if I put 1 joule in, I can get 1 joule back. Heat energy, not so much. The forms of mechanical energy where I get a one-to-one reciprocation are kinetic. They're elastic potential. How about I just put an E, or sometimes they'll use an S. Capital U is for potential. So elastic potential or spring energy, and gravitational potential. Well, there, we've exhausted. Those are the 3 forms of mechanical energy that we say we have a one-to-one reciprocation. Generally, what makes a problem go from a conservation of mechanical energy to just a general conservation problem in our class is kinetic friction. If there's kinetic friction, mechanical energy is not going to be conserved. Notice I said kinetic friction, not static friction. I'm being very careful because static friction allows things to roll, and therefore we still conserve mechanical energy. Only kinetic friction will strip away mechanical energy into an unusable form. Now, you can get energy back from heat. It's just not as efficient. We don't get a one-to-one reciprocation. So a heat engine will transform heat into mechanical energy, but most of the time they're very inefficient. And so we don't get a one-to-one reciprocation. We lose some of the energy in its useful form. So I want to talk to you about how we deal with conservation of energy problems. But to do so, you have to have an understanding that you're going to be given situations where you will have to identify whether energy is being conserved or not. And that's not always obvious. That's the part that I think is hard, is having to judge, is this a situation in which energy is a conserved quantity? And I'm trying to tell you from the onset that the best way is to just look at whether there's kinetic friction acting in your system or not. If there's kinetic friction, you will not be able to get the energy back out. But for the most part, if you can't identify any source of kinetic friction, it is very likely you can use conservation of energy. So here's the situation we're going to look at. We're going to look at a small child's toy that has a little car pulled back against a fixed spring. That's then going to be released to launch the car. The car is going to make its way to various places along the track. Hopefully, we assume. So can you guys imagine this? What conservation of mechanical energy says is that when we consider the various states of our problem, I just want this to be H. When we consider the various states of our problem, we believe that at these various states of the problem, the total mechanical energy of the system remains a constant. Instead of taking a look at how work is being done, we assume that the forces acting in the system are all acting cooperatively to preserve the total energy of the system. All we have to be able to do is identify where we believe the energy of the system is in each of these places. We know that each form of energy has its own way of maintaining quantity. For spring energy, it's how much the spring is compressed. If a spring isn't compressed, there is no spring energy. For gravitational potential energy, it's based on your height above the reference level, where the reference level tends to represent the lowest possible position that the object can attain in the path the object is traveling upon. And kinetic energy is the easiest. If it's moving, it has it. If it's not moving, it's not. Our job is to identify what forms of energy are likely to exist and link them all together. So when I look at a problem and I'm trying to decide whether I can utilize conservation of energy, I'm looking for springs, changes in height, and objects that are moving. Specifically, remember, in your problems, you're going to have to delineate when you can use conservation of energy and when you can't. And the best way is to look for changes in height and springs. Those signal conservation of energy. Movement's harder because momentum also is based on movement. So there's one or two important features that make a problem a conservation of energy problem. One is a change in height. The other one is the fact that you're observing one object at a time. For conservation of energy, we are only observing a single isolated object and its energy. If it bounces off something else, it's no longer going to conserve energy. So when we deal with conservation of energy, we can only deal with one object, one mass. Now, that being said, you should be able to look at this and tell me when it's traveling the fastest, when it's traveling the slowest. You should be able to figure that out without any numbers. You should also probably tell me when it's probably traveling the same speed, regardless of direction. Would you all agree that it's traveling the same speed at B and C? Does that seem reasonable? Does it also seem reasonable it's probably traveling the same speed at D and G, even though they're in different directions? That seems pretty reasonable. They're about the same height off the ground. I think it's traveling slowest at H. That seems to be where it's the highest. Second slowest at E. Second slowest at D and G. And probably the last aggregation there is going to be at F. Fastest, B and C. That kind of observation, nice and easy to make here. But the better thing is, I don't have to know about any of the forces acting in the system. If I want to know how fast it's going at E, then I can recognize that it has kinetic energy and gravitational potential energy at E. If I want to know how fast it's going, I just need to know the energy it has at any other state. But I'm going to have to be given at least one state. I need to know the energy at one of the states to do this. So they're going to have to tell me maybe how much the spring was compressed when I launched it, or how high it went at the end. That gives me something so that I know the energy at one state. Because once I understand the amount of energy at one state, I can apply it to all the states of the problem. Please notice, when I'm talking about conservation of energy, I am talking about states. Do you hear that? Now, conservation of mechanical energy is an ideal situation. It's not a real situation. Very seldom is energy actually fully conserved. Mechanical energy. Real situations almost always have friction, air resistance, or something else that changes the energy into a non-mechanical form. Yes, sir.
I don't think that those work for this pursuing.
All right. Well, you guys probably go. You know I don't pay attention to the stuff. So apparently it's the end of the day, and I wasn't paying attention. So, yay! Go to class. You're not